Okay, so today we're going to be looking at 4.7, which is modeling real situations using exponential functions. If you remember from the first lesson, an exponential function has a basic shape like this. It starts off slow and it quickly grows. There's a lot of things in real life that grow in an exponential way. For example, the population of bunnies in Fraser Heights. I almost ran over a bunny yesterday. They multiply like crazy. You start with 2 bunnies, and then after a year or 2 or 3, you have exponential growth in the bunny population. If interest rates are good, your money in the bank can also grow like this. For example, the basic compound interest formula. So most banks work in a compound interest way, which means that if you get interest over the year, then the following year you get interest not only on your money, but also on the interest that the bank has already given you. So the interest compounds. This is a formula that you're not given on any formula sheet, so it's important to memorize. The A represents the total amount of money that you have in the end. The P is how much money you start with. R is an annual interest rate, written as a decimal. N is the number of times that the bank pays you money. My bank pays me once a month. So for me, N would be 12. How many times the bank pays you money per year? And T is the total time. So for example, if you invest $2,000 in a Canada savings bond at 8% per year, find out how much money you will receive in 10 years. If the money is compounded annually. So compounded annually means that the bank pays you once per year. And that's just saying that N is equal to 1. The bank is paying you one time every year. So, what does 2,000 represent? Which letter? P is the principal. That's how much money you start with. The 8% is the interest rate, which we're going to write as a decimal. And we want to know how much money we have after 10 years. 10 years represents which letter? P. So let's plug that into the formula. The total amount is the principal times 1 plus the rate divided by the number of periods to the power of the number of periods times T. So the total amount is the $2,000. The 1 in the equation means that we're making money. So the 1 just means you get 100% of your money plus the interest. The interest is 0.08. We're doing this one time every year, and we're doing it for 10 years. Oh, I forgot to pull out my graphing calculator. There he is. So just plug in those values. I don't actually need to type the ones. And after 10 years, wow! I have $4,317. Calculator back. What's the decimal? 8085. So I got more than double my money after only 10 years. How awesome is that? Any chance that you can get 8% of the banks these days? Do you know how much percentage you can get in interest right now? 0.5 if it's a basic checking account. If it's a high interest savings account, High interest savings account means usually you have to like keep it in there for 5 years before you can take it out. So usually if you want to get more interest, you have to put it away and say, I'm not going to touch it for 5 years, I'm not going to touch it for 10 years, and then they'll give you a higher interest rate. So my high interest rate savings account is 3%, which, yeah, is that high? Well, you can even try and put in 3% and see how much money I would get after 10 years. Probably not going to double my money.
Let's do your banking.
So if you want to see how much money you get by compounding monthly, all you have to do is take the interest rate, divide it by the number of times you compound, and the power changes to 12 times the number of years. And this really doesn't change the amount of money that you make by all that much. It's kind of like the dividing by 12 and multiplying by 12 offset one another. So you get about $100 more. So it's 4439.28. So what initial investment needs to be made to become a millionaire in 25 years if you receive interest of 12%? Think of how many schools you could build in India with $1 million. Semi-annually means, semi means half, and annually means year. So you're getting paid every half year. That means 2 times every year. So we want the total amount to be $1 million. So we want to be able to solve for the initial amount and end up with $1 million. You guys would still be so young 25 years from now. If you can find a 12% bank account and money to invest, let's see how long it's going to, or how much money we got to start with. Okay, so the reason why I'm dividing by 2 here is because this is saying that each time I get paid, I'm getting 6%. So I'm getting 6% in June and 6% in January. And then I'm getting paid 2 times as many times. Over 25 years, I'm getting paid 50 times. So 1 plus 0.06 to the power of 50 is 18.42. So 1 million, and technically I should keep all my decimals here. Now move it over to the other side by dividing by 18.42, and it really doesn't take that much money. So your principal is $54,288. So if you put that $54,000 in the bank, wait 25 years, really high interest rate, that's the kicker, right? It's the high interest rate. Try the same equation at 2%. That's the interest rate that you can get nowadays. It takes a lot more money. Compounded monthly means that n equals 12. So same formula. And we probably need a little bit less money to start off with because we're getting a little bit more from having monthly compounding. For 2%? So we get 19.788. We divide both sides by the 19.788. $50,000, 560. Sorry. 535.68. Okay. So in example 3, we have Marianne. She starts with $3,500 in a Canada Savings Bond. The interest rate is 5.4% per year. Compounded monthly. Carlos starts with $3,000, but he gets more interest rate, but it's compounded annually. We want to know how many years will it take for the two investments to be equal. Yeah, graphing is a great way to solve this one. So we can look at Marianne. Marianne starts with $3,500, and her interest rate is, and we change it to a decimal, 0.054. And we don't know how many years it is. So we're going to put N for the number of years. Oh, sorry, T. The N represents the number of times that it's compounded. So because Marianne's is compounded monthly, that means N is 12. So we divide the interest by 12 times the number of years by 12. Carlos starts with $3,000. His interest rate is 6.8%. And we don't know the number of years. Because Carlos is compounded annually, that means that N is 1. So we divide the interest rate by 1, multiply the time by 1. And we want to know when will those two amounts be the same. So basically we're trying to find out when will Marianne's be equal to Carlos's. And you might need to write really small for this. I don't need to write the ones. This is hard to solve. It's very easy to graph. Okay, the problem with this one is that the t, the thing that we need to know, is an exponent. That means we need to use logs. Whenever you use logs, it's very important that you log everything. I can't just put the log anywhere that I want to. I can't just put a log in here. I've got to log everything on both sides of the equation. So log of the left equals log of the right. So logs will go around everything. Let me simplify that 0.054 divided by 12. Add 1 is 1.0045. And I can combine this one as well, 1.068. So ideally I want to use the power law to bring those exponents into coefficients. Unfortunately I can't yet because I've got two different bases. The 3,500 has an exponent of 1. And the 1.0045 has an exponent of 12t. So before I can move the 12t down, I've got to separate the two different bases. And again, you're going to need to write really small to fit this in. Okay, so I'll take it over here. So we're going to break this up using the product law. 1.0045, 12t. 1.068 power of t. So now that I have the bases separated, now I can use the power law to make the exponents into coefficients. And I kind of need you guys to help me with keeping my decimal straight. It really is 1.0045, right? I didn't make a mistake with my numbers, so I just had to memorize it. Okay, so now you're just trying to get all the t's on one side, all the things that don't have t on another side. So I'm going to move this one over to the left-hand side of the equation. And I'll move this one over to the right-hand side of the equation. Okay, and now that I have only t's on the left side, I've got a common factor. So I can factor out the t and write what's left over in brackets. So now that I've isolated t, I can divide both sides by all the stuff that's on the left. Now I wish I had a copy-paste on this. So by dividing, I cancel off everything on the left-hand side, and I'm left with just t. So now hopefully I don't get a negative number, because I can't have a negative number of years. I need my graphing calculator. There it is. So it's important to be careful with your brackets here. Put brackets around the whole numerator and brackets around the whole denominator. To get 12.94 years. So we'll just round that up to the nearest year. So after 13 years, those two investments will be equal. Okay, and you can also find the equation, or you can also find the answer just by graphing the two equations in your graphing calculator. And you just need to make sure to put brackets around the exponent. The first one was 5.4%, right? Okay, good. And then the second guy starts with $3,000. I'm going to use x's instead of t's. And then when I graph it, I need my window to go up to at least 20 years. And my y value is probably going to have to be really big, because I'm talking about a lot of money here. Okay, maybe not that much money. As long as I can see the graphs, then I'll be able to find the intersection. I think that might have been a trouble on your quiz yesterday, that you weren't able to find the intersection because it was off of your window. Enter, enter, enter. And the crossing point is 12.94. So that's a good way to verify your answer. Okay, now on the back side, we can also use exponential functions for population growth or when populations are quickly declining. So this is the second formula. If you take a look at the top of your first page again, this formula is used for populations, for growth and decay. And it has kind of the same form as the compound interest. On the left-hand side, you have the final amount. The first thing on your right-hand side is how much you start with, the initial amount. And C is your growth or decay factor. C equals 1/2 for something that's going down by half, like a half-life problem. C equals 2 for something that's doubling. C equals 3 for tripling. Okay, so C tells you how quickly something's growing. T is the total time. And P is the total time for the growth or decay factor. So P is how much time it takes you to grow, like to double once. Maybe it doubles every 5 hours. Then P is 5. So P is the period. So if the question says it doubles every 5 hours, that would mean that C is 2 and P is 5. And then it might ask you how much time would it take for the population to grow by 10 times. Okay, so we'll do some examples with this. So example 4 is a half-life problem. It's talking about radioactive phosphorus, which has a half-life of 14.3 days. And if we put some amount of phosphorus in the body, how long will it take for the level of radiation to drop to 5%? So we're going to use the A equals A naught C to the T over P. How much phosphorus do we start with? A small amount. It doesn't say exactly how much. How much phosphorus do we end with? 5%. So let's put 5% as the ending amount. Then A0 is the starting amount. If we end with 5%, how much percent do we start with? Very good. Okay, so even though we don't know the exact amount, we can write it as percents. We end with 5%, start with 100%. C is the rate, T is the total time, and P is the period. So let's see, how much is it growing or shrinking by in this question? It's growing or shrinking by half. It's a half-life. So after every 43 days, 14.3 days, the amount of phosphorus will decrease by half. So with any half-life problem, C is a half. Now we have to figure out the 14.3 days. Is this the total time or is this the period? Period. Because this means every 14.3 days, we have half as much as we began with. Okay, so 14.3 is the period. And we want to know the total time. So we can write these percents as decimals. And the trouble is, we have a t in the exponent again. So that means log both sides of the equation. I really don't have to write this 1 here. The 1 times anything is still that thing. So now I just have a single base on the right-hand side, which is good. I can use the power law to make the exponent into a coefficient. So log of 0.05 is t over 14.3 times log of a half. So to solve for t, I can multiply by 14.3 and divide both sides by log of a half. So t is 14.3 log 0.05 over log of a half. And again, you could just plug this into your calculator. You know, plug in both sides of the equation and see that it crosses at the right spot. If you have trouble with the logarithms, that's a good way to check your answer. And the total time is 61.8. So in 61.8 days, you'll have 5% left. Now, for a question like this, I always like to check my answer just in a really common sense sort of way. So I start with 100% after 0 days. It goes down to 50 after how many days? 14. And then how long would it take to go down to 25%? 28. And then another half would happen after 28 plus 14, so 42 days. And then it would go down by half again in another 14.3 days. And then half of that is 3.125. And that would be another 14.3 days. Okay, so my 5% is somewhere between these two. My 5% is somewhere in here. So my days should be somewhere in here. So my days should be somewhere between 57 and 71. It is. It makes sense. Okay, so you can use that sort of thinking on a multiple choice question. Okay, 2 more examples. So in 2002, university population was 160,000, increasing at a rate of 4.5%. How many years will it take for the population to double? How many people do we want to end up with? $320,000. So we want the total amount to be 320,000. We start with 160,000. What's the growth rate? .5%. So if we change that to a decimal, it's 0.045. And we want to know how many years will it take for the population to double. So in this case, we we can just say that it's growing this much at an annual rate, means that it's growing that much every year. So that means it takes just one period. The period is just 1 year for it to grow. We want to know the total amount of time. Now, I intentionally made a mistake in this equation, which Jonathan caught, right? What's that? Yeah, if the rate is less than 1, that means that it's actually shrinking. It's shrinking to 4.5%. So it's going from 100 to 4%, and then smaller and smaller each time. So in order for it to be growing, the rate has to be bigger than 1. So that means the 1 in front means that we have 100% of what we originally started with, plus an extra 4.5% every year. So again, the t's in the exponent, you've got to use logs. If you want, you can divide by the 160,000 to start. And that'll make the question much easier. Then you just get 2 equals 1.045 to the power of t. And the 2 represents the fact that we're waiting for it to double. And the p is 1 because it's an annual rate. It's happening 1 time every year. I'll continue over on this side. So now I can log both sides. And because I only have one single base, the t can move down to a coefficient by the power law. So to solve for t, divide both sides by log 1.045. And you get a total time of 15.74 years. Okay, the very last example comes from a past provincial exam. So just take a moment to try and see if you can figure this one out by yourself using the equation. So, a patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. That's the starting amount. And 24 hours later, the sample was recounted and found to have 8,012 cells. So that's how much she ended with. We want to find out what is the doubling period. So we're trying to solve for P. And we're told that 24 hours later is when we have 8,012. So that means that the time that they had to wait for the growth to happen was 24 hours. The C is kind of hidden in the words here. Because it's a doubling problem, C is 2. Now, I really recommend that when you start a question like this, you just divide both sides by the starting amount. It makes the logarithm so much easier. And I don't even have to simplify that. So log of 8,012 over 387 is log of 2 to the 24 over p. And now because I only have one base on the right side, I can bring the exponent down as a coefficient. So 24 over p log 2 equals log 8112 over 387. Because the p is in the denominator, I want to move it to the other side of the equation, and it times both sides by p. You want to do this anytime a variable is in a denominator. So 24 log 2 is p log 812 over 387. So now I can just divide the log 812 over 387s to the other side. To get a total of 5.5 hours.